Welcome viewers to the fourth segment of the fifth lecture from the online series of lectures for the course of Algebraic Topology 2. In the previous segment, we finished the proof of lemma 2. In this segment, I'm going to first suggest a few exercises for you. So here is a list of suggested exercises from the book from the textbook by Mancres, section 24. Problem number 1, problem number 2, problem number 5, problem number 6. In order to do problem number 6, you have to recall the definition of retraction from the course of Algebraic Topology 1. Recall the definition of retraction. From the course AT1. So there are several parts of this problem: A, B, C, and D. So D relates to finding a counterexample. Okay, and also problem number 7 from section 24. Okay, so these are all from section 24, and there is also a bunch of exercises from section 23. Problem number 2, which consists of 3 parts, A, B, and C. Problem number 3 and problem number 4. Try all these problems. There will be a final assignment. I plan to post the problems from this suggested exercise in the last assignment of the course. So it's time to get started with a very important sequence, exact sequence in algebraic topology called Mayer-Vittorius sequences. Okay, so let me erase everything. We don't need them anymore. So let's get started with Mayer-Vittorius sequences. So let me state the result by means of a theorem. This is the second theorem of this lecture. Let K be a simplicial complex. Let K0 and K1 be subcomplexes of K and let K0 and K1 be subcomplexes of K such that K is equal to the union of these two subcomplexes. Let A be the intersection of these two subcomplexes. Then there is an exact sequence HP of A to HP of K0 direct sum HP of K1 to HP of K to HP minus 1 of A. there is this exact sequence. Well, if you want, you can write the sequence in the following way. We should do it in order to keep track of things. HP of A to HP of K0 direct sum HP of K1 to HP of K, then from there to HP minus 1 of A to HP minus 1 of K0 direct sum HP minus 1 of K1 to HP minus 1 of K to again HP minus 2 of A, and goes on like that. Okay, so this is the long exact sequence. Okay, this sequence, so there exists a sequence like this, and which is called the Mayer-Vittorius sequence. Mayer-Vittorius sequence of the pair K0 and K1. There is a similar exact sequence in reduced homology. If A is non-empty. Okay. In other words, if K0 and K1 are not disjoint. Okay. All right. So this theorem needs to be proved. Okay. So this is the statement of this theorem. Now I'm going to erase it because I need room to prove this theorem, to get started with the proof, basically, because it's a long proof. It cannot be done in one screen. That needs to be erased, and it will take a while to prove this theorem. The proof, let me first let you know how we are going to prove this theorem. The proof consists of constructing a short exact sequence of chain complexes. Exact sequence of chain complexes. Okay. So from the trivial chain complex to C of A to C of K0 direct sum C of K1 to C of K to the trivial chain complex. Okay. All right. So remember, A is the intersection of the two subcomplexes, K0 and K1, and K is the union of those two subcomplexes. So K is a subcomplex which can be written down as the union of these two subcomplexes, K0 and K1. Okay, and the chain map um, um, from the chain complex A to the chain complex CK0 direct sum CK1 is denoted by phi, and the chain map from this chain complex to this chain complex is denoted by psi. So this has to be constructed first, and once we construct this short exact sequence of chain complexes, we apply zigzag lemma to get the result, okay, of theorem 2. So first of all, in order to um, construct this short exact sequence, first of all, one needs to define this chain complex. Define the chain complex C of K0 direct sum C of K1. All right. So it's going to be a chain complex. So it would be a collection of abelian groups, and the abelian group in dimension P is going to be Cp of K0 and direct sum Cp of K1. So its chain group is the direct sum of these two groups in dimension P. Okay. And so what's the boundary operator? So I need an operator that will take this guy to this guy. Okay. So what is that operator? Let us denote that operator by del P prime, and this guy is defined as del P prime is going to act on a pair, right? The first element of the pair comes from Cp of K0, which we denote by dP, and the second element of the pair comes from Cp of K1, which we denote by EP. Okay, and we define this as a pair whose first element is going to be del P K0 dP, right? So del P K0 is the boundary operator in the in the in this complex C of K0. So this consists of the abelian groups, which are Cp of K0, and the boundary homomorphisms are del P K0 there. Okay, so this is that boundary homomorphism. Okay, so this is going to be an element here, right? And the second element of the pair is going to be del P K1 EP, and this guy is obviously here. This is how we are going to define this boundary operator. Next, we have to define these two chain maps, phi and psi. How do we define these two chain maps? Next, we need to define the chain maps phi and psi. Okay, so we do it as follows. Okay, so let us number this equation by 9. So this is the thing when dP is in Cp of K0, which means that dp is a p chain on K0 and ep is a p chain on K1. Consider the inclusion mappings, in the following commutative diagram. Okay, so I'm going to draw a commutative diagram now. So I need to keep this diagram intact for a while. That's why I'm going to erase things from the right so that I can draw that diagram there. So let me erase everything here and draw that commutative diagram on the right. So A is, as we know, that A is the intersection of the two subcomplexes K0 and K1, and I have this inclusion of the intersection in K0, right? This inclusion is denoted by I, and on the right I have the intersection, on the right I have the union of these two subcomplexes, which is the whole complex K, and I have the inclusion of K0 in this union. And this inclusion is denoted by K. Then I have this subcomplex K1 here, and the intersection of K0 and K1 is included in K1 here, and the inclusion mapping is denoted by J, and K1 here is included in the union of K0 and K1, which we denote by L. So here, the intersection of these two subcomplexes, K0 and K1, is included in the union of these two subcomplexes in the obvious way, and this inclusion is denoted by N. So this figure is the figure 1 of this 5th lecture, is the commutative diagram, involving inclusion mappings, Okay, good. Now we are going to define, so phi, the chain map phi is a collection of homomorphisms. Okay, phi is a family of homomorphisms, so is psi. These are chain maps, so they are going to be defined by those members of the family, right? So I'm going to define homomorphisms phi and psi in the following way. So phi p, okay, well, remember that. So let me write the short exact sequence that we want to construct. This is the zero chain complex, and this is the chain complex C of A, and from C of A to C of K0 direct sum C of K1, and from here to C of k, and then from C of k to the trivial chain complex, right? We denote this chain map by psi and this chain map by phi. So we are defining phi. So phi p is supposed to be a group homomorphism from Cp of A to Cp of k0 direct sum Cp of k1, right? It's supposed to be like this. It's supposed to be a group homomorphism from Cp of A uh, to this group. So we are going to define this by phi p of Cp, where Cp is an element in this group Cp of A, and this is going to be equal to, right? It's going to be a pair because it will be here, right? And the first element or the first component of this pair is going to be I hash at P acting on Cp. So see this inclusion, this commutative diagram involving these inclusion mappings. And when you look at this inclusion map I, you see that I hash at P is going to be a map from a Cp of A to Cp of k0, right? And this is I hash of P, and J hash at P is supposed to be, J is this inclusion mapping, is supposed to be a group homomorphism from Cp of A to Cp of k1, right? And how about K hash at P? This should be a group homomorphism from Cp of k0 to Cp of k, and L hash at P is going to be a group homomorphism from Cp of k1 to Cp of k. These are 4 group homomorphisms by means of which we are going to define these 2 chain maps phi and psi in terms of the group homomorphisms that they consist of. Okay, so I hash P of Cp, where Cp is an element in this group Cp of A, will take Cp to here, Cp of k0. So this component is in Cp of k0. We are good. About the second component, we take minus J hash at P acting on Cp. For an important reason, we are taking this to be a minus. That will be clear later on. So J hash at P, it takes Cp of A to Cp of k1. So J hash P Cp is in Cp of k1 as expected here. So we are good. So phi p of Cp is here according to this definition. This is equation number 10. Now, how do we define psi p? Psi p is another group homomorphism which, well, look at psi p here. Psi is a chain map from this direct sum of groups to this chain complex C of k. So we expect psi p to be a map or a group homomorphism from Cp of k0 direct sum Cp of k1 to Cp of k, right? And define it by psi p acting on a pair this time. This pair is dp comma ep again, where we chose dp to be where dp is in Cp of k0 and ep is in Cp of k1. Okay, so dp is a p chain on k0 and ep is a p chain on k1. So psi p of dp comma ep is supposed to be in Cp of k. So we define it as k hash at p dp. Well, look at here. K hash at p takes Cp of k0 to Cp of k, right? dp is in Cp of k0, so k hash p dp is in Cp of k. This guy is in Cp of k. So similarly, L hash at p acting on EP, L hash at p is a map from Cp of k1 to Cp of k, right? EP is in Cp of k1, so L hash p acting on EP is in Cp of k. So there are two, two objects in Cp of k, and since Cp of k is abelian, we can sum them up there. So that's the operation in that abelian group. Okay, so this is how we define psi p. This is our equation number 11. So now it's important to check that phi is a chain map. We need to verify that it's indeed a chain map. So this is the definition of the group homomorphism phi p, and we need to check that indeed phi is a chain map defined this way. A is k0 union k1, k0 intersection k1, and this is the inclusion which we call I, and this is the inclusion of A in k, and here is k1, and the inclusion of A in k1 is denoted by J. This is I hash at P. Okay, so now we need to check that phi is a chain map. So we consider the following diagram. Recall that phi is a map from here to here. Okay, so if phi is a chain map, then the following diagram commutes. So this is a chain complex C of A. So we write down, so we draw this chain complex first. So dot 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 Cp plus 1 of A, and then to Cp of A to Cp minus 1 of A and goes on to the right like that. And this is the operator homomorphism del P1 A, and this is del P A. Okay, and here we have this group Cp plus 1. Now we are here in this chain complex, right? So we're going to write the abelian groups and form this chain complex. So dot 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 dot. This is Cp plus 1 K0 direct sum Cp plus 1 K1, right? And then to Cp K0 direct sum Cp K1 to Cp minus 1 K0 direct sum Cp minus 1 K1. Okay, so here is a map. So here is a map and there is a map. Okay, so this map is phi p plus 1 according to what we have here in this you know it's a sequence, and we want to prove that it's a short exact sequence. And this is phi p plus 1, and this is phi p, and this is phi p minus 1. Okay, so in order to prove that phi is a chain map, we need to prove that this is a commutative diagram. Okay, so how do you prove this? Show that the diagram above commutes. So we start with this thing. This is phi p composed with del p plus 1 a Cp plus 1. Okay, Cp plus 1 is here. So we are going from Cp plus 1a to Cpk0 direct sum Cpk1 via this path, right? So the resulting object will be here in this direct sum group. Okay, and this is going to be equal to, according to the definition of phi p, I mean equation number 10, according to that equation, it's going to be equal to the first component. So it will be a pair, right? Because it's supposed to be here. And the first component of that pair is going to be I hash at B, right? Del P plus 1 A Cp plus 1, right? That's the first component. And the second component is minus J hash at P del, again this guy, del P plus 1 A Cp plus 1. Okay, and this holds for Cp plus 1, this guy, in Cp plus 1 of A. Okay, now this is equal to, so we need a couple of commutative diagrams. We know that I hash and J hash are chain maps, right? Hence, they should commute with their respective boundary operators since they are chain maps. Okay, so we have this commutative diagram Cp plus 1 of A to Cp plus 1 K0, and then Cp of A to Cp of K0. So this map is a boundary homomorphism, del P plus 1 A, right? And this is del P plus 1 K0. And the top map is I hash at P plus 1, and the bottom map here is I hash at P, right? This is a commutative diagram since I hash is a chain map. Similarly, for J hash, we are going to have this commutative diagram Cp plus 1 A to Cp plus 1 K1, and then here Cp of A to Cp of K1, and from Cp1 of A to Cp of A, we have this boundary homomorphism del P plus 1 A, and this is del P plus 1 K1. This map is I hash at P plus 1, and this map, sorry, this is J. Okay, and this is J hash at P. So this is also a commutative square. Okay, so from these two commutative diagrams or commutative squares, we have the following. So I hash at P composed with del P1A, meaning that this path is the same as this path, right? So we write it as del P plus 1 K0 composed with this guy, I hash P plus 1, and this is Cp plus 1, right? Comma, this is a minus sign, and then from here J hash P composed with del P1A, meaning that we are going from Cp1 of A to Cp of K1, where this part, since this is a commutative square, is the same as taking del P plus 1 K1 composed with J hash at P1. Well, and that this composed map acts on Cp plus 1. Now, from the definition of this map, del P prime, remember, del P prime is defined as the following, in the following way. It acts on a pair, right? Del P prime acts on dp ep to give del P K0 dp, comma, del P K1 EP. This is how it's defined. So from here we see that this is equal to del prime P plus 1 I hash P plus 1 Cp plus 1, comma, minus J hash at p plus 1 acting on Cp plus 1, right? And from the definition of the map phi p, we have this to be equal to del prime p plus 1 composed with phi p plus 1 acting on Cp plus 1. So this is equation number 12. So this square commutes, right? So I did not write these maps, right? What are these maps? This map is del prime p plus 1, right? The boundary operator for this chain complex, remember? That was del prime p. And this is going to be del prime p, and the first one is del prime p plus 1. So we got the equation 12 tells us that phi p composed with del p plus 1 a is equal to del prime p plus 1 composed with phi p plus 1. So phi p composed with del p plus 1 a is this path by means of which we go from Cp plus 1 a of a to Cp of k0 direct sum Cp of k1. Okay, and this path del prime p plus 1 composed with phi p plus 1 is this path by means of which we go from Cp plus 1 of a to Cp of k0 direct sum Cp of k1, which means that this square commutes. Okay, now I need to prove that the square on the right hand side commutes as well. I leave it as an exercise. Okay, so the commutativity of the other squares can be done in the same way. All right. Well, it does not need to be done. It actually follows because they hold for any p. I mean that the square, this square. So just replace p with the other integers to get the commutativity of the other squares. Okay, so we're done proving that phi is a chain map indeed. So now we need to, so let me erase this. Now we need to prove that psi is a chain map. Psi is a chain map. Okay, so we need to prove that the diagram below commutes in order to prove that psi is a chain map. So here is the diagram. We have Cp plus 1 k0 direct sum Cp plus 1 k1 to del prime p plus 1. This is Cp of k0 direct sum Cp of k1, and from this to Cp minus 1 of k0 direct sum Cp minus 1 of k1 dot 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 dot. This is del prime p plus 1. This is del prime p. Okay, and then we have Cp plus 1 of k to Cp of k to Cp minus 1 of k, and goes on like that. This map is psi p plus 1. This map is psi p. This map is psi p minus 1. This is del p plus 1 k. This is del p k. Okay. We need to prove that this is a commutative diagram. Let dp plus 1 is in cp plus 1 of k0, and ep plus 1 is in cp plus 1 of k1 here. And then one obtains psi p composed with del prime p plus 1 dp plus 1 comma ep plus 1. Okay, so we are going from here to here. So we are going from here to there, so via this path. So psi p composed with del prime p plus 1 acting on an element here is equal to psi p. So from the definition of del p prime, the boundary operator on the top chain complex is given by this expression. So del prime p plus 1 is going to give us del p1 k0 dp plus 1, and the second component is going to be del p plus 1 k1 ep plus 1, right? ep plus 1. This is what we are writing using this definition, which was equation number 9. Okay, so from here, we know from the definition of psi p, it follows that this guy is equal to k hash at p composed with this thing, del p plus 1 k0 dp plus 1 plus l hash at p composed with del p plus 1 k1 ep plus 1, right? This is what we write. This is using equation 11, and this is equation number 13. Okay, so now note that this two maps, k hash and l hash, are chain maps, are both chain maps, and hence both diagrams commute in the both diagrams below commute. So what are those diagrams? Cp plus 1 of k0 to Cp plus 1 of k, and then here Cp of k0, and this is del p plus 1 k0, the boundary operator, the boundary group homomorphism, and this is Cp of k, and this is del p plus 1 k. And this map, what is this map? This map is k hash p plus 1, right? And this is k hash p. Right? And on the right, I have another diagram which proves that the other chain map, um, so the other map k l hash commutes with uh, the boundary, the respective boundary homomorphism. That's Cp plus 1 K1 to Cp plus 1 K, and that's L hash at P plus 1. And this is Cp of K1 to Cp of K, this boundary operator, and this boundary operator is going to be del P plus 1 K1, and this boundary operator is going to be del P plus 1 K. And this is L hash at P. This also commutes. Both of these commute. Both these diagrams commute. Since K hash and L hash are both chain maps. Okay, so from 13, one obtains psi p composed with del prime p plus 1 dp plus 1 comma ep plus 1 is equal to, we have this equation number 13. So from the commutativity of the diagram on the left, this can be replaced by del p plus 1 k composed with k hash at p plus 1 dp plus 1, right? So I'm going to replace this with this using the commutativity of the diagram on the left. And using the commutativity of the diagram on the right, I replace this with delta p plus 1 k composed with L hash at p plus 1, right? EP plus 1. Okay. So now from this, we have del p plus 1 k, this operator acts on this expression, k hash at p plus 1 dp plus 1 plus L hash at p plus 1 EP plus 1. So from here we have del p plus 1 k, and this, so using the definition of psi p, we write it as psi p plus 1 acting on dp plus 1 comma ep plus 1. This is our equation number 14. Okay. So equation number 4. So what did we start with? We started with psi p composed with del prime p plus 1, right? dp plus 1 comma ep plus 1, and we ended up with what we have on the right side of 14. This is del p plus 1 k composed with psi p plus 1 at dp plus 1 comma ep plus 1. So which means that psi p composed with del prime p plus 1 is equal to del p plus 1 k composed with psi p plus 1. Okay, so this is del p plus 1k, this is del pk, and you know, um, so what is this? What we have on the left side is this path, via which we go from Cp plus 1 k of k0 direct sum Cp plus 1 of k1 to Cp of k, okay, via this path. And del p plus 1k composed with psi p plus 1 is this path from Cp plus 1 of k0 direct sum Cp plus 1 of k1 to Cp of k. Okay. So which means that this diagram commutes. So in the same way you can prove that by varying p, you can prove that the other squares commute here as well, and hence I is a chain map. So we are yet to prove the exactness of that sequence. So we are studying this sequence, right? 0 to C of A, C of A2, C of K0, direct sum C of K1 to C of K to 0. Phi is a chain map, so is psi. So we have defined this chain complex, and we have a well-defined boundary operator in this chain complex. We have defined the chain maps phi and psi. Now with those definitions of the chain maps phi and psi and the chain complex C of k0 direct sum C of k1, we need to prove that this sequence is exact. Okay. All right. Let's do this. Since I hash at P and J hash at P are just inclusion of P chains, so from equation number 10, one finds that equation number 10 gives us the definition of phi p, right? One finds that phi p for all p is injective. Okay, so remember the definition of phi p. So phi p of dp comma ep is I hash at p dp and minus j hash at p ep. That was the definition of phi p. And since I hash at P and J hash at P are both inclusion of chain maps, this map phi P is injective. That is, the chain map phi is a monomorphism. This chain map phi, we have proved earlier that phi is a chain map. This chain map phi is a monomorphism. Okay. Now, we need to prove that the psi is an epimorphism. Okay, also let's do it. So let us now check that psi p is surjective for all p given d in Cp of k. In other words, D is a p chain on k. Write D as an integral linear combination of elementary p chains corresponding to oriented p simplices. Okay, we can always do that. So since D is a p chain on k, so there are this elementary p chains on k corresponding to the oriented p simplices of k, and you can always write the p chain D as an integral linear combination of those elementary p chains. Okay, so let's do that. And so while we are writing D as an integral linear combination of those elementary p chains, we figure out the part D0 that consists of those terms of D carried by K0. Okay, so in D, D0 is the part that is carried by K0. Okay, so obviously D is equal to D0 plus D minus D0, and since the union of K0 and K1 is K and D is a p chain on K, D minus D0 has to be carried by K1, right? So what is psi p d comma d minus d0? This is in Cp of K0, right? And this guy is, we have just seen that this guy is Cp in Cp of K1. So this is equal to, from the definition of psi p is k hash at p d0. Sorry, I think I missed it. This is d0. This part is carried by k0, right? This is d0. And d minus d0 is carried by k1. So d0 is carried by k0 and d minus d0 is carried by k1. So k hash at p d0 plus L hash at p d minus d0, right? Now, since k is just the inclusion map, right? K hash is also an inclusion map, so is L hash. So this is going to be simply d0, and this is going to be simply d minus d0. So we end up with d. This is our equation number 15. So we started with this. We started with an arbitrary element, arbitrary p chain on K, right? Psi p is a map. Psi p is a map that takes this abelian group Cp of K0 directs some Cp of K1 to this abelian group Cp of K, right? So we started with an arbitrary element here, D, right? And we found out a pair, D0 and D minus D0 here, such that psi p of D0 comma D minus D0 is equal to that D that we started with. It proves that psi p is surjective. So every p chain here, Cp of K, has a pre-image under the map psi p. So in other words, psi is an epimorphism. So we are done proving that phi is a monomorphism, and we are also done proving that psi is an epimorphism. We need to prove that this sequence is exact at this site. In other words, we need to prove that kernel of psi is the same as image of phi. Then we are done proving that it's an exact sequence. Then the remainder of the theorem. Then the theorem on Myrick sequence will be proved by applying zigzag lemma. Okay. So now let's prove the exactness at the point to check exactness at C of K0 direct sum C of K1. Okay, so let me draw this. Let me draw this short exact sequence first. This is C of A, and C of A goes to C of K0, a direct sum C of K1, and then to C of K to 0 via this map phi here, via this map psi here. Okay, good. Now, given Cp in Cp of A, so we choose a p chain from this group Cp of A, then I think I don't need the bottom one anymore. So let me erase that one. And now I'm going to need the corresponding commutative diagram at the chain level. So here is Cp of A, and then here is Cp of K0, and then I have Cp of K here, and then I have Cp of K1 here. And this inclusion is I hash at P. This is K hash at P. This is J hash at P, and this inclusion is L hash at P, and this is M hash at P. Okay, so psi P composed with phi P at Cp. Okay. is equal to psi p. So let us use the definition of phi p. Equation number 10. First, to have a phi p acting on Cp is I hash at p acting on Cp comma minus j hash at p acting on Cp. This is by the use of equation number 10, which is the definition of the map phi p. Okay, now by using equation number 11 or the definition of the map psi p, we have the following: k hash at p composed with I hash at p acting on Cp minus L hash at p composed with J hash at p Cp. This is by 11 or by the definition of the map psi p. Now this is the commutative diagram. This diagram commutes and this part commutes as well. So from the commutativity of this triangle, we have k hash at p composed with I hash at p is nothing but m hash at p acting on Cp minus L hash at p composed with j hash at p is the same as m hash at p here acting on Cp, and this gives us 0. Okay, so we are doing it for a certain value of p, meaning that we are here Cp of a to Cp of k0 direct sum Cp of k1 to Cp of k to 0. Okay, so this is phi p and this is psi p. So we just found out that psi p composed with phi p is equal to 0, which means image of phi p is contained in kernel of psi p. This is our equation number 16. Conversely, let psi p acting on the pair dp comma ep is, so psi p is a map from this direct sum of two groups to Cp of k. Okay, and let us choose psi p of dp comma ep is equal to 0 with dp belonging to Cp of k0 and ep belonging to Cp of k1. Okay, good. So that the pair dp comma ep is in kernel of psi p. Now psi p at dp comma ep equal to 0 implies k hash p dp plus L hash p ep is equal to 0. This is what we can write using equation number 11. That is the definition of the map psi p. Okay, and since both k hash at p and L hash at p are inclusions, k hash at p acting on dp gives us simply dp, and L hash at P acting on EP gives us EP. Therefore, dP plus EP is equal to 0. Okay, and this leads to the fact that dP is equal to minus EP. All right, now notice that we chose dP such that dP belongs here in Cp of k0. In other words, we say that dP is carried by k0, and we chose EP to be in Cp of k1, and EP is in Cp of k1, meaning EP is carried by k1, right? Hence, since dP, and since dP is equal to minus EP, dP and EP are both carried by the intersection of k0 and k1, which we chose to be A, which we denoted by A, right? So we see that dP in particular is in Cp of A. Okay, so it is important to note that this P chain dP belongs to Cp of A, so that phi P can be acted on, so dP can be acted on by phi P. Now using equation number 10, which is the definition of phi P, we find that one obtains phi P of dP is equal to I hash at P dP comma minus J hash at P dP, right? And since I hash at P and J hash at P are both inclusions, it results in the pair dP comma minus dP. But we have earlier noticed that dP is equal to minus EP, so it's nothing but dP comma EP. Okay. So this is equation number 17. We call it equation number 17. And therefore, from 17, it follows that this pair dP comma EP is an element in image of, so we have proof that phi P acting on dP produces this pair dP comma EP, which means that dP comma EP belongs to the image of phi P. And this way we prove that kernel of psi P, because we first chose dP comma EP belongs to kernel of psi P, and we ended up showing that dP comma EP is in image of phi P. Therefore, we have proved that kernel of psi P is contained in image of phi P. And this guy, together with equation number 16, tells us that image of phi p is equal to kernel of psi p. In other words, um, this sequence here is exact at this term, okay, at this middle term. Okay, so altogether we have that this sequence is a short exact sequence. Okay, good. Then we can erase this part. So the homology of the chain complex C of K0 direct C of K1 in dimension P equals HP of C of K0 direct C of K1, right? Which is, of course, because the boundary operator is del prime P, so it's going to be kernel of del prime P modded out by HP. I think I made a mistake here. It has to be so they need to be corrected in the note as well. So this is kernel of del prime P, and so this is CP of K0 direct CP of K1, and by the action of del prime P it goes to CP minus 1 K0 direct CP minus 1 of K1, and there is del prime P plus 1 from CP plus 1 K0 direct CP plus 1 K1. So kernel of del prime P here quotiented out by the image of del prime P plus 1. Okay, and this is going to be equal to kernel of del P K0 direct sum. So I'm decomposing del prime P. Okay, and we know the definition of del prime P, and from that it follows that the kernel of that map is the kernel of the boundary operator in the complex C of K0 direct sum the kernel of the boundary operator in the complex C of K1 del PK1 kernel of del PK1 modded out by image of del P plus 1 K0 direct sum image of del P plus 1 K1. Okay, so it's a very easy exercise to show that this can be done. And recall from the abelian group essentials studied in the course of algebraic topology 1 that G1 direct sum G2 quotiented out by H1 direct sum H2 is isomorphic to G1 over G1 quotiented out by H1 direct sum G2 quotiented out by H2 whenever HI is a subgroup of GI for I is equal to 1 and 2. right? This is the case because this guy is a subgroup of this guy, and also this guy is a subgroup of this guy here, and hence we can write this thing to be isomorphic to kernel of del p k0 modded out by image of del p plus 1 k0 direct sum kernel of del p k1 modded out by image of del p plus 1 k0, right? And this is nothing but hp of k0 direct sum hp of k1. This is our equation number 19. Okay. All right. So what have we seen so far? Let me erase everything. So these are the things that we have found so far. We have constructed a short exact sequence of chain complexes 0 to C of A to C of K0 direct sum C of K1 to C of K to 0. Okay. This chain map is denoted by phi, and this chain map is denoted by psi. So we have shown that this is a well-defined chain complex with a well-defined boundary operator, and with with those definitions, phi and psi can be defined appropriately so that phi and psi are also chain maps. Okay, and with those definitions, this sequence becomes a short exact sequence. I mean that this sequence becomes an exact sequence. Okay, and given this exact sequence of chain complexes, one can find the pth homology group of the chain complex in the middle to be isomorphic to hp of k0 direct sum hp of k1. Okay, and now in the zigzag lemma, choose C to be C of A, which is nothing but C of K0 intersected with K1, and D to be C of K0 direct sum C of K1, and E to be C of K, which is nothing but C of K0 union K1. Okay. If we do so, then the zigzag lemma tells us that there is an exact homology sequence, and which homology sequence is as follows. There is this hp plus 1 k0 union k1, from which we have this goes to HP of K0 intersected with K1, and that goes to HP of K0 direct sum HP of K1, and that goes to HP of K0 union K1, and again that goes to HP minus 1 K0 intersected with K1, and then goes on like that. Okay, right. So this is the Mayer-Vittorius sequence when we are considering the absolute homology groups. Okay, now for the Mayer-Vittorius sequence, in the context of reduced homology, so we'll do that in the next segment. Okay, so we have been able to prove the Mayer-Vittorius sequence for absolute homology, for the case of absolute homology groups. Okay, good. Thank you for attending this fourth segment of the fifth lecture.